So we want to find the area under the graph of 2x on the interval of 0 to 3. So it maybe helps first to visualize a tiny bit how this graph might look like. So if you have 2x, it's probably going to look something similar to this. And if we have 3, let's say here, then we want to know the area between the x-axis and the graph. So this here. And we can approximate this area by dividing this into small rectangles. So they could look something like this. Why rectangles? Mostly just because it's really easy to figure out what the area of a rectangle is. Because, as you remember, the area of a rectangle is just the width times the height. So if we know each individual area of these rectangles, we can just sum them all up. So basically our area is just the sum of our small rectangle areas. Of course, it's just an approximation, but we can make this better later on. So the first thing we have to figure out is actually what the width of these individual rectangles is. And this depends actually on how many rectangles you have. In our case, we're just gonna have n rectangles. So if we have n rectangles, then we have to divide this width of 3 over n rectangles. And then we have the individual width of each rectangle. So each of these is 3 over n wide. So that's the first part. So we have the width. But now we actually want to get the height as well. And the height, as you can see, is the function's value at all of these x points here. And this first x point is just simply 3 over n. The second x point is 3 over n times 2. And this third one is 3 over n times 3. So in order to get the height, we just have 3 over n times something that we can change as we sum along. And in this case, this thing is called I. So now we already have all the parts that we need for our sum. So let's write that down. So our sum will be the function's value at 3 over n. And we can use I here as our iterator. So I changes with every times we make a new addition to our sum, basically. So this is the height. And then we still have to get the width, which was 3 over n. So this would be the area of n rectangles. But of course, we have to somehow specify how many rectangles we actually want to have. And for our case, it's actually pretty cool if we can have a lot of rectangles. So if you imagine that we have a ton of tiny rectangles here, then our approximation gets actually better. So the more rectangles we have, the better our approximation. And there's a tool that we already know that we can use for this, which is called the limit. In this case, we want to have many of them, so we can just say that n, so the number of rectangles, should go to as many as possible, as infinity. So this is basically what we want to solve now. This is our area. Okay, so the first thing we should actually do is replace this function here with our actual function up here. Because right now, we just have a placeholder. So we just want to replace the 3 over n times I with the x. So in this case, we have 2 times 3 over n times I, and then the 3 over n that already was there stays there. Okay, so this is our first step, but we can simplify this a bit more by just multiplying this term out. So because we have 2 times 3 over n, or 3 over n times 3 over n, we get 3 over n squared times 2i. Okay, so this is our term, or our limit. And now we want to figure out how we can make this a bit simpler again. So with Riemann sums, with sigma notation, there are a couple of rules that you have to keep in mind to make these easier. And one of them is that if we have some kind of sum, when we have a constant and some number k, then we can rewrite this as c times the sum of k. And this basically just means for us that we can put the 3 over n squared in front of the sigma. So we still take the limit, but now with the 3n over squared front, then still times 2i. And we can do the same for the 2. So we're just left with an I on the right side. And right now you might be thinking that it seems pretty weird to take a limit of the sigma thing. So people have figured out how we can rewrite this part here in a way without the sigma notation. So we can say that the sum of I just becomes n times n plus 1 over 2. So this means for us that we can just replace our part of the sigma notation with this part. Okay, so this looks a lot more doable already. And now we can just multiply this out to make it a bit simpler. So we can start with the 3 over n squared, which just becomes 3 squared is 9 over n squared, and 2 times 9 is 18. So we have 18 over n squared, and then we can multiply out the n in the second part. So it's going to be n squared plus n over 2. So this just becomes 18 n squared plus 18n over 2n squared. And now we can actually find the limit of this. So in order to find the limit, we want to divide by the biggest number in either the either the numerator or the denominator. So in this case, our biggest number is the 18n squared. So let's go ahead and do that. So we can say that this is 18n squared over 18n squared plus 18n over 18n squared times 2n squared over 18n squared. So the first one just results in a 1. The second one will result in a 0. That's because if we're taking the limit against infinity, if the lower one, the denominator is bigger, we're going towards 0. So it's 1 plus 0 over 2 over 18 with the same factor and exponent. So it means this will just leave us with 2 over 18, which will leave us with 18 over 2, which is 9. So in this case, 9 is the area under the graph, so between the x-axis and the graph.